Martin Bridgeman from Boston College, and the title is slightly different from what it says in the program. It's the same talk.
Okay, it's the same talk, but just a different.
Yeah.
Thank you to the organisers for inviting me. Happy birthday, Francis. We were colleagues for 2 years, so I've known Francis for a long time. And I've been spending most of the last few decades milking his theorems, so I'm especially happy to be here to thank him for that. And I'm going to continue doing that right now. So, okay, so what I'm going to talk about is, so we're going to talk about some objects that were discussed by both Jean-Marc and Fanny today. So, first of all, I'm going to start off with Quasifuchsian space. This is going to be representations of some surface into PSL2C, where they're QC conjugate to some Fuchsian representation. And then we're going to just quotient by conjugation. So if you have an element of the group, you have an associated length function, which I'm going to think of as a real valued function from Quasifuchsian space. And just because I'm going to be talking about the eigenvalues, you can write this if you think about writing in terms of diagonalizing the element. You can define it to be just, I guess, twice the log of the absolute value of the eigenvalue. Okay, so that's one object I'm going to be talking about. And so the first part of the title is simple length rigidity. And what happened, we were working on something in the second part of the title, and then we needed a fact in the first part of the title. And so it may be of independent interest, so I'm going to state that first. So the theorem is that if you have two elements in Quasifuchsian space, and with the lengths equal for all alpha simple, that implies that, well, x equals y, or x equals y bar. It's conjugate, the conjugate representation. So that's simple length rigidity. And we believe the argument works for AH of M, where M is asymmetrical. And where the statement is that, i.e., if xy in AH of M, and the lengths are equal for all alpha boundary elements of the boundary, fundamental and simple, then the same thing holds. So that's sort of one part of what I wanted to talk about, and give you some idea how you prove this, kind of a little bit of brute force. But where it arose was in what was now sort of an application, is that if you have so if we look at Quasifuchsian space, so there's a natural pairing, and I'm just going to call it J on Quasifuchsian space. And I'll describe what this is in a moment. So it's a pairing, where it gives you a real number. And I'm going to define F from Quasifuchsian space to itself. It is an isometry of J if it is an immersion and preserves J. And J of Fx, Fy, is equal to J of xy. And so, I'm going to call this and so the isometries of J. And so the corollary of this theorem is that if you have that the isometries of J is the mapping class group, well, it's the mapping class group generated by the mapping class group and complex conjugation. So you can sort of see this will come into bear in this dichotomy. Okay, so that's what I'm going to talk about. So before I do, I'm going to just talk define what this object is, but I'm going to define it in a little bit more general setting, which sort of relates to what Fanny was talking about. So, we're going to consider representations rho from some group gamma, any hyperbolic group or surface group G, where this is a finely generated hyperbolic. And G, I'm just to make things simple, G is going to be some matrix Lie group. And you can take the S out and or. And so if you have an element of, you can talk about its spectral radius. This is just the maximum over the eigenvalues of the absolute value of the eigenvalues. So that's the spectral radius. So it's a measure of the size of it. Okay, so you can use this object to sort of build.
Warren, can I ask a
yes.
question? Why can X equal Y bar? Doesn't the marking remember the orientation?
Well, first of all, they have the same letters, right? So if you
X is not a Riemann surface in this notation, it's a representation.
it's a representation.
Oh, yes, yes.
They're just points and representation. Just rather than writing rho with a square bracket around it, I'm just talking, that's the representation conjugated.
Representation conjugate. Okay.
Okay.
Yeah, great. It's not the.
X can be a representation. It can be, so anyway, I'll be using X and Y as well, rather than classic representations. But yeah, so that's, they obviously have the same lengths on simple. If you're just taking the real part. Okay, so we're going to build an intersection number using this. And
How do you do that?
well, this is part of sort of our work. Right. So this is a paper of myself, Dick, Francois, and Andres. So what do? So you first of all, you want to define a length of an element. And so you just define that to be the log of the spectral radius. And then you start doing sort of basic like counting ergodic theory using this as your length function. So first of all, so you define or make sure which notation I use, or sub t of rho. It's going to be the set of all constant classes of elements where the length of the element is less than equal to 0. So that's the object that when we have an Nassau representation grows exponentially. And so then we look at this exponential growth rate, so we take the limit as t goes to infinity of 1 over t times the log of the number of elements in 4 sub t. This is called the entropy. So that's the entropy of the representation. And so using the entropy, so in particular, if we were in the Fuchsian setting, this object would be constant, it would be just 1. But in Quasifuchsian, it's the Hausdorff measure. And in general setting, it's just something else. But the measure is exponential growth rate. So then we define for rho 1, rho 2 representations, we define the intersection number, the first intersection number, to be just equal to the limit as t goes to infinity of the 1 over the number in or sub t of rho 1, summing over all the elements in or sub t of rho 1, L of rho 2 of so all G and so that's your intersection number, and you hope it exists. And then finally, the J I defined turns out to be just a normalization of this. H of rho 2, H of rho 1, of I of rho 1, rho 2. So this object has some nice properties, and this is the intersection. I'm going to consider. And I'll give you another formulation that's due to Francis. But let me just sort of.
As given it's 1 or
What?
as given it's 1 for rho 1 equals rho 2.
Yeah, so it's 1 for rho 1. That's so you normal order. Yeah, it's 1 for rho 1 equals rho 2. So now we'll just define j sub rho be equal to j of rho dot. Okay. So in particular, as just pointed out, it's 1. It turns out some facts. J sub rho equating to 1, and the minimum at rho. And so we, I'm going to, if some family rho 2 is smooth, I'm just going to define what this, the pressure form. It's just going to be defined to be what's the length of this. It's just going to be the Hessian of this right now. So that's the definition of the pressure form. So So what is this? So it turns out that this is, we can do this in many different settings, and some of them have been done. And so you can reinterpret it, for example, for Tightware space. We have the following, and this is due to Wolpert, and the way I'm writing is Francis's reinterpretation of it, is that this the pressure form equals the Val-Pearson metric. It's the Val-Pearson metric divided by a constant, so it means divided by squared or the absolute value of all the factors. The normalized Val-Pearson metric. So that's a beautiful fact, and so it's originally due to Thurston's idea for a new metric that Wolpert showed was the Val-Pearson metric, and Francis reinterpreted using geodesic currents, which is sort of the way I sort of like to think about it, and the way I'm going to sort of describe it now. So, okay, so getting back to, yes?
So the fact that you wrote this, that's supposed to be obvious, right? That was the theorem.
What's it? This is so facts that, yeah, so I'm going to, this is a, let me just, I'll put that as a theorem. I know these guys, I'm not going to get upset. No, but yeah, so that's, so the fact about the pressure, I think we wrote up in our paper. Okay, so, right, so that's the pressure form, and we know a theorem that's related to this as well, due to Maser and Wolf, is that the isometries mod S is the isometry of W on okay. So what we did was we showed that the pressure form is a Riemannian metric on the Hitchin point. And that's mod S invariant, and WP on the Fuchsian locus. So, so that's one of the main results in our paper. So part of this sort of is to sort of investigate and see about hopefully proving something like the isometry group of the pressure metric is mod S. And so, any questions? Yeah.
The minimum for the intersection number is it only attained in
yeah, it's only attained at one point. But okay, so originally I'd studied this through a different formulation using geodesic currents, and which corresponds to basically the showing that the pressure form on Quasifuchsian space is first of all, it's a Val-Pearson on the Fuchsian locus. That's easy. That's and not S invariant. But it's not a Riemannian metric. It has some degeneracy. But it's positive definite of the Fuchsian locus. So it has this and the length of a vector, the pressure metric, is 0 if and only if V is an element of the unit tangent space, Quasifuchsian space at X, where X is Fuchsian, and the V is equal to I times W, where W is actually in the Fuchsian locus itself. So it's in the pure bending directions. If you think of this box-shaped Behr's mutation, here's the Fuchsian locus, and here's V, and here's W, and this is I times W for something going wrong. Okay, so that's okay. So I want to consider this intersection form on. I want to consider J on Quasifuchsian space. And to do so, I'm going to have to sort of introduce GD's occurrence. So these were introduced by Francis. And so what are they? So you've got a space of GD's. The space of GD. And if you have, if you've got some surface, some hyperbolic surface, and a GD is a current, S is a gamma invariant measure on So you consider the action of the fundamental group on the space of geodesics. And the typical examples are essentially the only two examples I know, which is you say alpha closed curve, alpha tilde splits, and then put the rack measure on alpha tilde. So you let mu alpha equal that, and that's a gamma invariant measure. So that's the way to think of geodesic currents as being containing closed geodesics. And the other example is if you're thinking of a measure and you've got some intervals of geodesics, just take the measure of that to be the only thing that you know is you take the log of the absolute value of the cross ratio. So if I get this wrong, A minus C, B minus D, A minus D, cross ratio. So this is called the Liouville. Now, denoted by, this is going to be, actually, I'll denote it by mu of the surface. Actually, MLS. Okay. So, any questions?
Why do you need absolute value?
What?
Why do you need absolute value?
Well, because I might be careless and it's not positive. Yeah, I don't think you do need it. You're right. Yeah, it's at least one. You don't need two of them. Okay, so where am I going? Okay, so we look at this. If you have if x is hyperbolic, x is now in the Teichler space, you have is the space occurrence of GD's occurrence for x. And it turns out if you've got two of x and y going in T of S, then obviously the spaces are equivalent by push forward or pull back of measures with the identification with their limit sets. Okay, so and you also you have also for alpha an element of pi 1 of x. You have you have a function L of x on the space of currents on x2 or, which just actually not it's defined in all G. This is just equal to 11. This is well defined, and so I should say the theorem in parentheses. So there's the intersection I on closed GDs extends to a continuous I from the space of currents to R, and such that from I of alpha with the Liouville measure is just the length of alpha in S. Okay? And okay. Okay. So right. So this gives a function L with a space of currents across Teichler space 2R, where you essentially L of alpha x is just the length of alpha in x. Okay. So that's a sort of general length function. It's smooth when you fix on the alpha, and it's continuous on the space of GD's occurrence. Okay. So this is also going to parentheses, is that if you look at the Weil-Pearson metric at x is just equal to taking the Hessian of the length of function due of the Liouville current at x. So that's the formulation that I like to think of in terms of the Weil-Pearson metric. Okay, so if you're now in Quasifuchsian space, how do you? So you can reformulate J as J of xy on Quasifuchsian space. J of xy is it's the ratio of the Hausdorff dimensions of two spaces times the length of certain GDs occurred in Y. And what's that GDs occurrent? Where, so this is the Hausdorff dimension of the Lie set. And mx is a generalization of the Liouville current. This is the unit length Patterson-Sullivan GD is equivalent. So this is just a reformulation. It's there's a generalization of the Liouville current to convex but compact by Patterson and Sullivan. And so this is just an GD current that sort of represents the dynamics of the action at infinity. Anybody any questions?
When you take the intersection with a current, with a closed curve current.
It's a what?
When you take the intersection of mx with a closed curve.
Yeah.
Does it give you the length of the geodesics in the Quasifuchsian manifold represented by x?
So if you have if you're looking at this, yes, if you take the length of a closed curve, yes, you get the length of the closed curve. Okay. What? The length function here extends to a length function on Quasifuchsian space. Yeah. So if you take a curve, you actually take a curve, and so there's a generalized length function.
It's a question about intersection.
All right. Yeah. The intersection number. No.
No, the intersection.
Well, if you make it, no.
The intersection between mx on a current.
Oh, on a closed curve. No.
It does not give you the length of the.
Yes. No.
Okay. There is no current which does that. There.
I don't think so. I'm not sure. That's not the sort of the defining property, but no. Okay. But okay. So how do we go about proving? How does this? How does simple length rigidity come into showing what is the isometry of this object? So the first thing to note is, so I'm going to break it up into a number of steps. So what are we doing? We're showing that the isometry of J is equal to sort of this mod S with some allowing complex conjugation. So what do you do? So the first thing to observe is that if F is an isometry, then as it's an immersion, or well, actually, so as it's an isometry of this, that implies in particular F is preserves the pressure pull. So that means in particular that F has to preserve the the zero locus of the pressure point. So we already showed that, I already stated that the pressure form on Quasifuchsian space has these bending directions which are zero. So this has to preserve these zero vectors. It sends zero vectors as zero vectors. That implies in particular that F restricted to the Fuchsian locus is a map from the Fuchsian locus to the Fuchsian locus. And it's isometry of the pressure metric. The pressure metric restricts to the Val-Pearson. So it's an isometry of the Val-Pearson. So that means that in particular that F restricted to F of S is some G lambda of S. So that's step one, to know that. And so step two is just to observe and say, okay, I can assume by post-composing that G, that, so step two is just assume F is equal to the identity on the Fuchsian locus. So just assume it's the identity in the Fuchsian locus. And because we can just do that by step one. And if we do that, then what we have is we take X in the Fuchsian locus, and Y be some generic element of Quasifuchsian space. So then we know that J of xy is equal to J of x f of y. F of y. Because F, it preserves J. And what this says is that L of mx in y is equal to the Hausdorff dimension of f of y over the Hausdorff dimension of y times the length of m of x in f of y. So it's saying that whenever you have a Patterson-Sullivan GD's occurrent for an element of a Fuchsian locus, then the lengths of those things in both spaces are the same, are up to a multiple.
I think I'm getting confused. So MX before was the...
Oh, no, yes.
MX was Louisville in the Fuchsian case, but
It's Louisville and the Fuchsian, it's Patterson-Sullivan. It's actually going to be Louisville because we're picking X to be in Fuchsian, so it's going to go back to be Louisville again.
Okay.
So we don't even, so that's why I don't even have to tell you what Patterson-Sullivan is, because it's Louisville again.
Okay.
So we're back to being...
But is it? It's a continuous on QF?
Yeah.
As you move off the Quasifuchsian slice to...
It's, yeah, so it's you get a map into the space of currents of Quasifuchsian space.
Okay.
Into a Patterson-Sullivan. Yeah. I think that's due to us. Okay, so what? So now I'm going to. I told you I was going to be using theorems a lot. So what theorem do you think I'm going to use now? Well, if you look at a map from Teichner space, where you send X to its Louisville current projectivized, the projectivized Louisville current, this gives the first compactification. So this gives you Thurston compactification. This is the image is you can take the closure of the image because the projective current is compact, and this gives you the Thurston compactification by measured lamination. Okay, so that's great because I don't know what the Liouville currents are, but I know where to limit to. So step 3 is that alpha be simple in S. And then just let mxi tend to the class, the projective lamination given by alpha. And what does that mean? That means there exists some Ci going to infinity, but Mi or Ci is going to alpha bar, which is in this projective class. And that implies, in particular, by continuity, that the length of alpha in Y is always the ratio of the Hausdorff dimensions times the length in each. Okay, so that's step 3, and now we've got something we can just we can skip out and say, okay, if I prove that that can't happen, then I'm done. And so that's the reduction of the problem to what turned out not to be an easier problem. So we define the following. X and Y in Quasifuchsian space are K simply related. And this is almost as bad notation as witness, but only a joking, that's not you, that's right. No, it's pretty bad. But if Lx of alpha is equal to K Ly of alpha, did I switch the alphas? Yeah, okay. For all alpha simple. Okay, so that's the so what we want to prove is that this can only happen if X and Y if K is 1 and if K is 1 and they're either equal or constant. So that's the next phase. So the next thing to prove is 1, prove that K is equal to 1, and then 2, prove simple relations. Okay, so that's the idea, the structure of the proof. Anybody any questions? Okay. So we have some time to get into a little bit of the weeds of the proof. So how do you go about proving something like this? Is you try and get enough curves so that you get contradiction, and but you have to always be making sure you're staying simple. So that's the idea. Okay. So the first element is X and Y are in Quasifuchsian space and are K simply related. and K. So let me just give you a sketch. So particularly, I'll just write a corollary. What the corollary of this is F in isometry of J implies F preserves Hausdorff dimension. And the length in X of alpha is equal to the length of Y alpha from alpha. So the proof of this lemma is kind of a simpler version of the general proof. The general proof requires a little bit more computation, but it's sort of the same spirit. So what do you do? So let's just sketch this. So you have two representations, and you choose alpha and beta, simple, intersecting of alpha and beta equal 1, so you have to be non-separating, and we think of rho I of alpha and rho I of beta as some. And then you just play with. So what is this? What do we have? We have that we can take gamma n to be equal to alpha to the n beta, and we can now just look at. So we look at lambda I of n is going to be just the eigenvalue, the eigenvalue of rho I of gamma n. Okay, and then you note that you have the equation that lambda 1 is equal to so you get an equation like that, and so you end up you end up expanding both these in terms of so you write these in terms of the traces, and you end up with some equation, and the equation, you get some equation that says, whichever one is bigger, you get the real part of lambda 2 over lambda 2 r to the minus 2m a2 d2 1 over a2 squared is equal to 0. You get some equation like that. That limit has to be equal to 0. And then you just do some playing around with saying, is this rational or irrational? And then you're essentially rotating this number around the circle, and then you try and use your information to get the fact that you get a contradiction, and then you get an equation that this gives you that k has to be equal to 0. And what we used in this was the fact that you had some expression on either side, and one of them is bigger, it's growing at a different rate, And so one term goes away and one term remains, and so this has to be 0. So that's sort of the idea behind it. Yes. What?
K equals 1.
K equals 1. K equals 1. Okay, so, and then I'll just sort of like roughly sketch out what the rest of it is what goes into the other parts is that it's pretty easy to do something similar to get the following letter. If x, y are 1 simply related, so 1 simply related, then you get either one of 3 possibilities, and you get that for an alpha is some simple non-separating, then you get that the eigenvalue of alpha squared or the conjugate, or there's a weird case that you end up doing now. And both are real. You know. So you end up doing this. So the next stage is you run this argument again now, knowing that k is 1, so you get actually that this term, the limit of this, is equal to the limit of the same thing for the other object. And now you have to play with that and see that you can show something about the eigenvalues. And then what you get is this object, and then you have to say, in some ways, these 3 conditions one can't happen for 1, and they all either have to happen or one of the top 2 are the only things that happen. So that's sort of the first key lemma is just to show that that's the 3 possibilities, and then the last one is just to. So then the final one is you have the corollary of this, I guess. So you have if the x and y are 1 simply related, then either there exists some alpha simple where either 1 or 2 happens for all beta, such that beta intersection of alpha and beta is equal to, because that's not, and beta is simple, non-separated. So that's the next stage is either 1 happens or 2 happens for all of them, and then you build and you show that the representations have to be equal or constant.
Inside the proof, how do you recover?
What?
Inside the proof of the lemma, how do you recover the complex?
All right, so how do you recover the complex? So to remember this, so what you end up doing is you let's see. So to show that one of these 3 things happen, I can remember it. So the eigenvalues have the same. So right. So here's the point. The point is the eigenvalues have the same length because k is equal to 1. So then you're rotating by some rotation here and rotation there. And you're asking how the rotation is the same. You've got some fixed number and you're rotating it. And if they're both irrational, well, they both either have to be rational or irrational because you can't have a finite number of points or infinity. So then if they're both irrational, then you can pick sequences where they're different if they're not the same. And so you get everything just by doing that. And turns out there's a weird case where this is -1. and you're both imagining it's just going boom, 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 with zeros and boom, boom, and that can happen, but it doesn't really. So that's the last case. Okay, and so I'll stop there.
Any questions?
Yeah.
You mentioned that you expected the scientific probably in the humans to come back asymmetrical case.
Yes.
Is there an intuition for it to fail with if you have some cylinders?
If you have some cylinders, well, I think that it's not really well defined. I don't know if the boundary subgroups is not really defined what it means in that case. I think it's harder to pin.
And you get this kind of rigidity for representations in other groups, then
So we're thinking about the same argument. You know, it's the same thing happens when you look at. Well, I think you could run the same argument and try and do it for hitching. And where you get, it would get a lot more complicated. But I think SL3 should be easier than the Quasifuchsian case, is my feeling. But I don't know. So I think you could do it. You get something, but you might find out it's not enough. Right?
So there's this conjecture of codage, I think, that if a group has, if you look at only lengths of simple closed curves on a surface group, and they don't, there's no any laminations, they're all proportional to their word length, then the representation is Quasifuchsian. So that also only looks at simple curves and only looks at the real parts of the length.
Oh, okay.
Could these techniques, I mean, these are, maybe this was one of the break in that.
So what's the group he's looking at?
Take any representation of a surface group and use it to see.
Okay.
You don't know it's discrete, but the simple, the lengths of simple elements behave as if it's discrete. Is it really discrete? That's the question.
No.
So this argument, with certain assumptions, this argument for defining the discrete case. Go ahead and tell me. I don't think it shouldn't detect discreteness in these techniques anyway. You're just looking at asymptotic values of traces and things.
I mean, there's some issue with this not being true for general representation, right? I mean, I don't know if you...
Right, so you have to look at the possibility of representation.
Yeah, I'm assuming the representation is...
I don't think these techniques should care so much about the discreteness. These techniques can work fine if you do the element of hyperbolic. Then the whole proof you never see. You never see anything. You just go free as it.
Okay. Let's thank Martin again.